K8 BYP on a rainy day, so I can't go out and play antennas. And good and bad news to report on the Drake TR4. I found a design screw up, a big one. Drake really, what, the pooch, and never caught it. Because this TR4 was 10 years, maybe more, past the TR3, and the TR3 has the same flaw. I went through the final stage in the TR4. I fixed the load capacitor. The back section of the load capacitor was bad. It's used by itself on 10 meters with all the load current going through it. That correlates with a bad 10 meter crystal. So the rig was used on 10 meters a lot, and it wore out both parts. So what I did is took the center section of the load capacitor, which was good, and I connected it and used fixed value capacitors to make up a difference. And that works fine. So didn't have to spend $150 for a replacement capacitor. Orrin Elliott has replacement capacitors. They're obviously Chinese stuff, because the old prices from Cadwell, I think it was, would have been about $300 for the capacitor. But I digress. What you're looking at is the mixer 6AG7V4 in both the Drake TR3 and TR4. In the TR3, it was a 6HS6 replaced by a 6AU6. But anyway, I fixed the load capacitor. I went through the voltages on the final stage, perfect. Except for a serious problem with V8, the front final tube. I put the 3 tubes in series filament off a 15 volt supply set to about 17 plus. And that front tube, which was an RCA with 2 Westinghouses, was way out on filament. The filament voltage was 5.7 instead of about 6.3. So I fixed that by changing the tube and put in a bigger power supply, higher voltage. So 18.9 volt string, about 6.1 to 6.4 on each of the final tubes. That's good. So a thing to watch out for. Filaments ought to be in parallel so each can draw its own current. And that is what tube matching is about, not matching gain or transconductance. That's an old wives' tale. But here to Drake's serious screw up. The TR3 and TR4, both flaky power output, varying 10, 20, 30 watts. The more I'd test the TR4, the more the power would drop much of 30 to 50 watts. That's way too much. That's the equivalent of one final tube not working in the AR. The transmit gain control is not right. It's going to a max at a bit over 9 o'clock. It should go nearly to 11. That's just low drive. So I went through the stages, went through the voltages, and something I had missed, because I assumed Drake couldn't even screw this up, but they did, is that they misdesigned this rig and the TR3 to destroy this mixer tube. And this is the mixer. It's a pentode. The screen grid, control grid, and cathode are a triode, and the screen grid, suppressor grid, and plate are also a triode. They're electron coupled, and that brings in the signals from the 9 megahertz carrier and the mixed output from the local oscillator and the VFO into the grid of V4. And the plate circuit is coupled into that inside the tube, and that's the mixer. The 6HS6 and 6EJ7 have extremely high transconductance. This tube is like 15,000, and the 6HS6 is upwards of 17,000. Way high. In other words, really high gain. What was really funny about this V4 stage is that in transmit, the plate voltage went up, and it can't do that. In receive, the cathode's biased high to cut the tube off. The voltage was 230 something. And in transmit, the voltage went up at 4 or 5 volts, and that's impossible. Because when current flows through the plate with those two 1500 ohm resistors in series, it will cause a plate voltage to drop, but it wasn't. So with a grounded suppressor and a screen through an unusually low resistance of 1.5K, that proves that the current is coming from the screen. Well, that's a warning. That's a danger sign right away. It can't come from the grid. Grid can't draw that much current. It would fry it instantly. And the screen voltage on this tube was about right, and that's how I missed it before. But I didn't stop to check the drop across R22, which was from a 165 volt supply instead of 150. It's too high. It's unregulated and varies with line voltage, and line voltages are much higher than they used to be. In the TR3 and TR4 documentation, it goes up to 165. There's the flaw, because when this 150 volt supply is 165, that's 14 milliamp through the R22, 1500 ohms, and 14 milliamp into the screen at 142 volts, which is a watt dissipation, and that screen's only good for 9/10 of a watt. So it vaporizes the screen and deposited the screen material all over the inside of the tube, so the tube envelop's black. The cathode voltage is right. Plate voltage is quirky. This was a really easy one to miss, and I had missed it in a TR3. But this tube is where the transmit power is made with the correct drive. So this stage is critical. The understanding and practice of how to at least measure tube circuits and how to design them is pretty much a lost art. So I'm going to show you the basics of it on paper, because this is too sloppy to read. So maybe you heard that extremely loud thunder boomer. That's why I'm in the house. Here's the basic schematic for this tube. 3K plate, 1500 screen. The screen's typically 10K or more. Grid leak bias, 330K, 600 some K to ground. That allows a small electron flow through that resistor to self-bias the grid negative. Well, in this rig, that's not the case. In this rig, the key either opens up and allows a minus 65 volt supply to bias the grid off, or keys down to put the grid at 0. Well, 0 is a landmark for these small tubes because many of them can't operate at or plus side of 0. They'll be destroyed. So generally, these little tubes can only operate from 0 grid voltage to minus a couple volts, generally 5, 6, or 8 volts minus. Cathode, 2.5 volts, 330 ohms. The key here is that it's impossible to measure with a scope probe the plate or the grid because of capacitive loading. So all the measurements have to be made at the cathode. Ergo, the cathode resistor. There's two ways to bias a tube, either a negative bias on the grid and ground the cathode, or in reverse, a positive bias on the cathode and a 0 voltage on the grid, for example. 2.5 volts plus on the cathode is exactly the same as 2.5 minus on the grid. So that shows the operating point for the tube, and you can look on the plate curves, the tube data, for grid voltage versus plate current, and that defines transconductance, which is a figure of merit that's more or less gain. 2.5 volts DC divided by 330 ohms is 7.6 milliamp. 7.6 milliamp through the tube includes the screen current, because realize the cathode is the source. But approximately speaking, that is excluding the screen. If the screen current's very low, and the screen's the 165 through the 1500 ohms, it's the second set of dashed lines from the bottom. But if the current through the cathode resistor is plate current, and that's 7.5, 7.6 milliamp, then that times 3K ohms in the plate is, or yes, multiply that by the plate resistor and get a voltage drop of 22.7 volts, which makes the plate at about 220 volts DC. So let's take that 220 that's on the plate. There's 220 volts on the plate. And with 220 on the plate with 7.6 milliamp through the plate to cathode, that implies a plate resistance of 29K ohms. That is the main part of biasing the tube. And this is how, with 1, 2, 3 voltage measurements in this circuit, And knowing two resistances from a schematic and a calculator with just Ohm's law, we can calculate whether that tube is working correctly or not. Now, as far as the AC swing, because this stage is worthless without AC drive, which is actually RF, that tube is biased at minus 2.5 volt. That's the midpoint. So if it's class A, then that signal can swing minus 2.5 volts to take the grid to 0. And if it's a symmetrical AC wave, it can go up 2.5 volts. So without measuring the grid, because we can't, because the scope will kill it, we see that the peak-to-peak voltage input maximum is twice the cathode voltage. It probably won't be exact, but what's happening here is that AC swing into a very high transconductance tube. So the grid, the cathode, doesn't necessarily have to swing all the way. But we might expect to see maybe 4 volts peak-to-peak RF across that 330 ohm resistor in the cathode. The problem with this stage is the 165 volt. These screens at 142 volts from a 165 source through 1500 or across 1500 ohms is a 23 volt drop. 23 volts divided by 1500 ohms is 15 milliamp. That should be how much the plate current is, or maybe less. Take 142 volts, 42 divided by 0.015. That means the screen is 9500 ohms. That's low. The problem comes from the screen dissipation, because 15 milliamps times 142 volts is 2.1 watts. And according to the datasheet for the 6EJ7, the maximum screen dissipation is 9/10 of a watt. That's more than twice the dissipation. And that's why it's fried the screen. So if you think about it, way too much current through the screen. That's what's causing the anomaly with the plate voltage increasing when the tube turns on. So if you think on that, you can probably figure out what's happening inside the tube. Well, if the plate voltage is increasing, that means that there are fewer electrons from the cathode reaching the plate. But the cathode current is only 2.5 minus 330, which is 7.5 milliamp. Where is the other 7 milliamp going? And it isn't going through the plate because the plate current is decreasing. Well, the elephant in the room is that the screen grid is shorted or coupling to the suppressor grid, which is grounded. So if this were the case, if I were to unground that suppressor grid, I'd probably see a significant current on the suppressor, because the screen grid and the suppressor grid are close together. So serious mess up in a Drake TR3 and 4. The way to fix it is not redesign the stage. When the 165 volt supply is put at 150, the biasing is correct. So their major mistake was that and this is the only tube, I think, in the radios that has that low of a screen resistor and that much screen current, because it's a mixer. In the TR3, the carrier oscillator and the detector are in the same tube. It might also be similar. But in normal conditions, that screen current is maybe 7 milliamps. That isn't much current. So the mistake they made was connecting that screen supply to the unregulated 150 volt source, when they should have connected it to the regulated 150 volt source at the 0A2. And I measured the 0A2 current in the TR3. It was about 25 milliamp out of a max of about 30. So taking this 7 or 8 mils off the 0A2 will actually cool the 0A2 down, because it won't be dissipating as much energy. So somebody made a serious mistake in manufacturing by connecting this screen supply to the wrong source. So if you're chasing why the TR3 and TR4 power is down, it's very likely this tube is fried, and putting another one in is going to immediately fry it also. Speaking of the trouble with the filaments in the final tube, there's two ways to destroy a tube, particularly the heater or filament in the cathode. That's too much heater voltage, which simply burns up the heater and the cathode. But the sneaky way, it's not a UFO, it's a reflection from the lights behind me. The sneaky way is not enough heat, not enough temperature, that causes cathode poisoning. And to show you just how close amateur radio is to rocket science, this is a research paper on ion thrusters used for space travel. And in this paper, we see evidence to expose the myth in radio that heating the cathode causes an electron cloud to be formed, and that violates the laws of physics. And that violates the laws of physics because at that point there's no external fields to pull the electrons away from the cathode surface. But I'm going to show you proof from the research, from the scientific research world, that proves that that name is false. These ion thrusters are essentially vacuum tubes with directly heated tungsten filaments as the cathode that produce electrons for a plasma discharge. Same thing happens in vacuum tubes. And this is operating in the vacuum of space. Due to the high work function, there's the critical phrase, work function of tungsten. Tungsten, the material, has a high work function. Filaments had to be operated at temperatures of over 2600 K in order to emit electron current densities in excess of 1 amp per centimeter squared. And if you want to Google this paper, it's Goebel, Goebel _06 chap, CHAP6 cathodes.pdf. It's from a textbook. But vacuum tubes work by thermionic electron emission. The cathode is heated, and external potentials between the plate or the other elements and the cathode cause the electrons to be pulled away. The electrons are not pulled away just because the material is heated. But the critical point here is just how sensitive tubes are to the correct filament or heater voltage. 5%, beyond 5%, they're destroyed. And for broadcast tubes, they want it closer to 3% after adjusting for optimum. But this is the what's called the Richardson-Dushman equation. J is a function of a constant, and T squared. So these cathodes are a function in their heating of T squared, and if you draw the squared function, it basically tries to go straight up. There's an extremely fast change in the T variable for changes in voltage, to put it simply. Change of filament voltage just a little bit, it makes a big difference in temperature. So that's why vacuum tube heater voltages are critical. And here's a fact that shows that the radio idea of heating the cathode produces a cloud is proven false. In the presence of strong electric fields at the surface of the cathode, there have to be other fields. The potential barrier that must be overcome by the electrons in the material's conduction band, which is on the cathode, is reduced, which results effectively in a reduced work function. So heating the cathode reduces the work function. Otherwise, a couple hundred volts difference from plate to cathode couldn't move any electrons. This is what's called the Schottky effect. The cathode of tubes is coated with, it's either could be tungsten or I think it's barium something or the other complex chemicals. The properties of the materials selected for the thermionic emitter, which is a cathode, determine the required operating temperature of the cathode for a given emission current. And a broadcast engineer in North Carolina told me that the 6 JB6s in the Drakes are valuable because their cathodes can source an extremely high amount of current. They were used in television high voltage horizontal output stages where they had to switch quickly and supply a huge amount of current. And contrary to another ham myth about sweep tubes and not being fit for RF, they are exactly for that purpose. They're good for up to 110 megahertz. There's a mention of oxide cathodes, which I think many of our receive tubes have work functions under about 2 eV, produce high emission current densities, temperatures under 1000 C. Barium oxide deposited on tungsten or nickel films to lower the work function and reduce the heater power required. These surface layers evaporate and are easily sputtered by ion bombardment that happens in space. And this graph is an example of how quickly the emission current changes with temperature. Each horizontal line is a factor of 10. And you can see the lines they're not quite vertical. So with a small change in temperature, there's a huge change in cathode emission. But here is where the tubes are destroyed by cathode poisoning. Because chemistry is involved in the formation of low work function surface, cathodes are subject to poisoning that can significantly increase the work function, which means more temperature or electrical force is needed. Care must be taken to handle so that the cathode isn't poisoned by impurities in the gas that produce unreliable emission and shorten the life. And that can happen from excess current bombarding the other elements like the plate. If the getter doesn't get it, then those atoms, those ions, are free to travel around, and that cathode is extremely hot. So these days, it's essentially a no-no to connect any of this old tube equipment to an AC line and operate it. It's going to destroy the tubes, because a modern AC line voltage under ANSI standards is 116 to 126. And all this old equipment, like the Drake's, was designed in the era of AC line voltages of 105 up to 110, 116, 117. So the modern line voltages are 10% higher, and that's way beyond the tolerance for tube filaments. So it's a must to correct a filament string or use a variac or do something, or have a supply of tubes to replace when they fail. So there's the big story about the Drakes and tubes, and more tube theory than you'll get anywhere else. KBYP did it.